All right, let's begin. So today we're going to talk about control theory, and this is when we will kind of officially talk about when poles of a system are on the right-hand side of the complex plane. Maybe a quick review of that is in order. Right? When we do the Laplace transform of HT, right, we turn that into the frequency domain. We have a real and an imaginary part. And when we say poles on the right-hand side, really what we've done so far is that if I have a pole, right, it has a real bit and an imaginary part. And what the real part is less than 0. That's pretty much what we've been doing all along. However, we have talked about integrators, which will start off today's conversation, where that's 1 over s and the pole equals 0. All right. But, you know, we're going to spend a lot of time talking about the transfer functions, right? And this is really a Laplace domain type things, where Bode really was a Fourier type thing, because we were plotting along this axis, right, where we were substituting j omega into h of s, where we're setting the real part equal to 0. And in fact, the frequency response is taken from the negative imaginary to the positive imaginary, but the Bode plot only takes the positive, right? And we actually plot it on a logarithmic scale, and we just calculate the magnitude and the phase. So even though you use the Laplace transform to find the transfer function that ultimately you use the Bode plot, when you say this, right, you're really saying that there is some kind of sine wave and you're inputting a sine wave into the system, and that sine wave has always existed and will always exist. Okay, just a quick review there. So the Fourier, there's a Fourier transform, right? We've been working on the expansions. Anyway. So really, without control systems, and really we're talking automated control systems, because you could be a control system, right? If you drive a car, right, you're putting your foot on the pedal, right? Might not be gas any longer. You could have an electric car, right? You're controlling the steering wheel to where things should go, and you're controlling the brake. So you are a control system. But you're not really automatic, right? You have to do it. It won't take care of itself, right? So we're talking about automatic control systems. And without that, it would be very hard to have manufacturing or just about anything. And this has been true for a long time, right? Other things, problems with humans, is our reaction time is about 280 milliseconds. And some things need to be controlled faster than that, right? But of course, all this great automation, right, that we can save us time, money, lives, right? Is it stealing jobs, right? even right now, right, when you talk about artificial intelligence, that's really just kind of a control system, right? Or an automatic way of making a decision. It's a nonlinear system, or or when it is linear, it's based on a lot of statistical equations, but and most often implemented on some kind of digital device, right? But the idea of the first control system that would control where a ship was headed rather than the sailor manually, I want to say steering wheel, but a ship doesn't have a steering wheel. And there was a lot of pushback to say that no machine could take into account the current, the wind, and various things to get it to work. Autopilot is a control system, right? So these have been around for a long time, right? And yeah, if you remember the second Charlie in the Chocolate Factory, right? Charlie's dad was put out of work at the toothpaste factory because a robot was now assembling the cap on the toothpaste. Now, of course, at the end of the movie, he becomes the maintenance worker for the robot. Now, what they fail to point out is that maybe, if you hire one robot to do one person's work, right, and then hire them back, the economics aren't so great, right? Helm, yeah, thanks. There's a number 2. Hey, Corinne, not quite sure. Oh, maybe what you mean, Corinne, is there's a number 1. All right, there's the old Charlie and the Chocolate Factory movie, right? And then there's the new one. Okay. If we have time, I'll go show you. I'll pull up a video of the old one, but the new one I think is a lot better. But it's the same book. Okay. All right. So, here's an old school, control system that, would have been something that mechanical engineers learned, right? And it's just not electrical. The thing is as time goes on, right, it's just so much easier, faster, better, more accurate, more reliable to control things electronically, which is why controls is pretty much centered in electrical engineering, right? But in this particular figure, what's going on is that you've got an engine here that's speeding, right? And what'll happen is as the engine goes faster, these balls will swing out, which will start to close off this valve, thus either reducing the fuel flow or oxygen flow, and so it'll slow it down, right? And or you could think of it as in terms of an oven, right? Is that when you set your oven to 450 Fahrenheit to bake an apple pie, right? The oven heats up. There's a temperature sensor inside, and when it hits 450, it turns off the heating element, right? Without that automatic control system, the oven would turn on the heating element, and it would keep heating until it either, exploded, or it would reach some maximum value that might change on the temperature, the ambient temperature of your room, or things like that, right? And our bodies are control systems, right? Now, basically, there's a thing called a microcontroller. The Arduino is one, right? Which is an environment that helps you get started with microcontroller development. High school students, middle school students, it's easy to pick up, right? Now, as an EE, though, you need to really know what's going on the inside and be able to program it more efficiently, right? So the Arduino IDE is really not where you want to be for your senior project, right? But most control is done with a digital microcontroller, and the way it interacts with the environment is with analog to digital converters and then digital to analog converters. And in fact, our project in 110 Lab is to make a digital to analog converter that takes a pulse width modulated signal, right, and turns it into some kind of DC value. Right, Stuxnet was it infected programmable logic controllers, right? And there were, I've read science fiction novels where like military mercenaries would use analog electronics because they couldn't be hacked, which, yeah, but they're not very flexible. Although you can have electronic tuning, although there is a system that you can dynamically control what's going on the inside in an analog system. And long story short, this is a field programmable analog array, and all the filters and gain stages that we've been doing with op amps, you can do with switch capacitor circuits and actually change the effective values of resistance and capacitance, right? Your filter cutoff points and gains on the fly. So, maybe not quite unhackable. All right. So even though, right, we'll be controlling in the, the digital domain, discrete time, discrete valued, many of the things that we are going to control are the outside world, which are continuous time and continuous value. And so even though we use analog to digital converters and digital to analog converters, it's really helpful to start this topic in 110, right? Now if control systems are really your thing, you have a choice. You can take EE 132, which is control systems. If you really like communications, that's 160. But 110 kind of gets the conversation rolling for both these areas. You have a choice between 132 and 160. You can take both and have one count for your technical elective. But we also have a lot of technical electives for microcontroller control systems. All right. In the end, though, you kind of have to know both because, if you're really pushing the limits of what can be done, you're using the advantages of the digital system and the analog system. Now, that was a whole lot. Oops. Any questions before we get going? So let's try to just talk about, what is control theory in general. And here's a signal flow graph, right? And it's kind of what I talked about. You're controlling the temperature of your house, or you're trying to. Hey, Nick, that's a great question. I think actually I'm going to cover it in depth later in this lecture. Okay. But no, I think polls gives everybody a hard time. So, of course, now you could think of this as a Nest controller that we're controlling it with your smartphone, right? But essentially you're sending in a signal, a voltage that represents temperature, right? And the voltage isn't directly proportional to temperature, meaning, it's proportional to temperature, but not that 40 volts equals 40 degrees C or 70 volts equals 70 degrees Fahrenheit. There's some scale factor going on in there, right? And it goes into the summer, right? Now here we're calling this the error signal, but if this looks kind of familiar to the DF2 design, well, it is, right? Here's the thing though, that heater, right, is really just a mathematical transfer function. The room temperature really is like V out of the filter. And then you have these feedbacks, which we were integrators, right? And so we were making a filter with a kind of a control system, or we were making control systems out of filters. But what's different is that you're controlling something that isn't an electrical signal. So you have the heater, right? A whole heater system. You have a temperature sensor that converts it back into some voltage that then the controller can make a decision, right? Now, this is something, open loop, right? Meaning there's no feedback, right? So open loop would be if we just got rid of this temperature sensor, right? And here we're providing a feedback. Before with the DF2, it was always integrators. Now it can be anything. G of S can be actually a constant, right? Which was, right? We had used H of S of, the system transfer function of op amps. And then we had a G of S, which was really the ratio of two resistors. And we got a non-inverting gain circuit. But what's really interesting is that when H of S and the feedback systems, right, it's almost as if that error signal is the high pass node. Might not be true, but just looking at it, seems like it. Of course, you don't know what HS is, all right? And so, really, this equation here, where YS, that's the output, right? You have the input times this transfer function, right, divided by 1 plus G of S, H of S. And we've kind of already done that, right? Now, the system itself, since we already used H of S, we're going to use a new name called Q of S. Now, in the past, you might have seen me say HS of the op amp, right? And this would be HS of the system. But in controls, we're just using a Q here, okay? Now, we keep talking about control, but there's a phrase that you're going to see in life and on your exams and things like that of like, is that system in control, right? What does that mean? So that reminds me of, there's a contest that IEEE has with students called Micro Mouse, and they have to build a little robotic mouse that goes through a maze to get from one space to the other, right? And one year, a group made a little robot that basically randomly bounced around. And this random bouncing thing actually would sometimes win. But if you put in an input and get some random output, that's not really in control, right? If you put in an input and the output just keeps increasing no matter what, that might not be in control. But really, the easiest test is to put in a step input. And if it settles to a DC value, it's in control, right? Now, now the thing is there's some signals that can actually trick you into thinking, oh, that's in control. But really, you can't fool the step response. But yeah, if your signal starts at DC and ends at a DC non-zero, and the system goes to some constant value, then it's in control. Yeah, Manuel, you're right. You're right. Not to make fun of anything, but yeah. So let's take a look at some system that we've actually been dealing with quite a bit. And that's where h of s equals 1 over s. Now, a lot of times we're talking about ut, right, which turns into 1 over s in the s plane. But really, h of t isn't really ut, it's really the integrator, right? Because this implies that we're convolving it with something. So yeah, it might be 1 over s might give you ut, but the whole implication is we're putting a signal into a system. So there's this convolution, right? So let's just do an example. One we might have seen, we could even call this a review. We have our signal, a ramp, right? It's ramping up, and at time equals 1, we start ramping down, and then we flatten out. Okay. So then, as a review, right, there's 1, 2, 3 things, but rather than deal with 1, 2, 3 Laplace transforms with 1, 2, 3 delays, really, we're going to have RT convolved with UT. So I just find the 1 and then substitute in, right? And so I look at this and I have something squared, then it'll even out, and then it will end up here. Can be a little bit difficult to see here, but when you plot it, right, here's my input. I go up and down, start and end at 0. Here's my input, a step, and the blue is the output response. Starts at 0, ends at a DC value. Could be in control. You know, you said if I put in a kind of a step response or a DC value, or if your output ended at some DC value, it could be in control. Well, this is a bit of a trick question. Let's go back to the step response, right? Which was in fact FT common, right? Ramp times Laplace of the ramp times the Laplace of the step, and we get RT squared here. So right away, I'm putting in I start at 0, I go to some non-zero thing, step response, non-zero DC, right? My input is going up, and my output is exponentially Well, not, I mean, some squared, right? So it's increasing. Well, can I say that I'm actually out of control, right? Well, here's my step response, the impulse response. But notice, while before I started and ended at 0, so I looked like I'm in control. Here, well, the input keeps increasing, right? So if the green is an integrator, well, the area underneath this is just going to keep increasing, right? So it looks like it's out of control, but it could be the system is out of control, but it also could be that the input isn't bounded. It just keeps increasing. So I can't really definitively say what's going on here if I didn't know what was going on up here. Okay. So now, and I might have misspoke up here. This is still the same, but it's not the step response, it's the ramp response. Okay. Now I'm doing the step response. And just to orient you to this particular slide, I'm having the step response delayed by 1. That's just so you can see what's going on, right? So if I had the step input and the step impulse response, these two lines would be over each other and you couldn't tell. So I just delayed the input. And so now I delay it, and here's the output, right? The input starts at 0 and ends at a non-zero value, and my output just keeps on increasing, right? And it's right here. Shows you it's a ramp. The ramp goes up forever until something happens that isn't modeled, right? And here, right, what I've got is an input of a step, and then I add another step to it. And so I'm increasing, and then I keep increasing some more because it's 2 delayed steps, right? So it just keeps going up. So this is not in control, all right? Because that step response is causing an output to keep increasing, even though you can kind of make it look like something is controlled by carefully choosing your inputs. Basically, if there's an input that makes that output increase, then it's not a control. Well, I'll take that back. The thing is start and end at some non-zero value. So really the rule is you cannot have poles with a real part that are equal to 0. So now I'm going to come back here. So here's our transfer function. All right, it has a denominator polynomial. Nope. Numerator polynomial and a denominator polynomial. And we're really concerned with the denominator polynomial, right? So a pole or poles are values of S that cause H of S to infinity. Okay. I think Nick's got a good question there. And so convergence kind of means something else, but basically settling to a DC value, right? And so this settles to a DC value, sure, but it's because I carefully selected the input. The system itself, right, is inherently out of control. It just isn't demonstrating it at this time, right? Maybe like maybe I'm an out of control person, right? But because the Umbrella Academy is on, and I really like that show on Netflix, that while I'm watching it, I'm in control. I'm I'm nice and I'm not snapping at people. But as soon as the input is off, right, or they talking about canceling it, I start getting mean to people, right? Inherently, I might not be demonstrating being out of control, but it's kind of like an identity. You are a system that is not in control or out of control. Okay. So poles or values of S that cause H of S to go to infinity. So let's just say, oops. Yeah, no, I meant to say the denominator of S is S, right? So when S equals 0, right, omega equals 0, right, then 1 over 0 goes to infinity, okay? So this is just one way, right? Now, something that I just want to mention, right? If this is my denominator, right? And the damping factor is greater than 0, omega naught is greater than 0, right? Then still I can have real poles, two real poles, okay? I'm just going to move some things out of the way so that I can see it. In this case, I have two different real poles, right? They're both on the left-hand side. And what we normally call that is an overdamped system, which is really saying 2 damping factor omega naught squared is greater than, okay? Now I can have 2 repeated poles, and that's saying that 2 times the damping factor times omega naught equals 4 omega naught, right? But still, that real part, they're both real, and they're both less than 0. And then I can have this, right? And I'm just going to draw that up here. Well, now we've got complex poles. Oops. And it's less than 4 omega naught. But the real part is still on this side, right? So having complex poles, right, doesn't mean that you're out of control, all right? Okay, so at this particular pole, what makes this 0, thus the whole thing go to infinity, is when s equals minus a. So we're out at minus a, right? Might be here, we've already talked about it, right? We have a pole at 0, right? Which we've already talked about being out of control. And then here, oops. What makes this go to 0? A. Okay. So all these poles are real, are not complex. They're purely real, right? But these two are not in control, right? And you can have complex poles on the 0 axis, and that's not in control either, but that's another example. But so Nick, did that answer your poll question? Okay. So for the first thing, how do I know this is not in control? Right? Right, we did examples on that. Now I'm going to talk about why this isn't in control coming up. Right, but we can see that a system with a pole at 0, right, isn't going to be in control, although sometimes it can look like it. Right. Now, oops. Looks like one of my slides got deleted. So I want to come back. Do that by hand. Okay. So let's say we have a system. Okay. And So that is exponential growth, which is, sure, if you've invested in a company, you like to see that, right? But in other cases, you don't like to see exponential growth. And certainly the stock market is not a control system. But it's really just a function of the inverse Laplace transform. It's just normally, this is what we see. Right, and I'm sure we can put it in the UT as well, right? But that's pretty much it. If you have anything on the right-hand side, you're going to get exponential increase. And it doesn't matter if you have 3 poles on the left-hand side and 1 pole on the right-hand side, that exponential growth is going to dominate and your system is out of control. And this works, right? I've been using kind of the low pass examples, right? Where this is like a, that's like a low pass type thing, right? But I could do S minus A as well. It's still out of control, right? So for a high pass filter, you have delta minus exponent e to the minus AT, but this system's out of control. So it's delta t minus e to the AT, and yeah, there should be a that should be there. Okay. And so you get that same kind of sharp increase like with a high pass filter, right? But a high pass filter will come back down to 0, right? So it does go up, but then we got this exponential increase and it's subtracted, so it just keeps getting bigger and bigger and bigger, right? Now, ultimately, with our op-amp-based circuits, it'll go to the positive supply rail or the negative supply rail and then just stop. But that's not really being in control. Okay. We all good with that so far? Now, so what we need to do, we need to be able to do after taking this class is look at a system and determine whether the system is in control or out of control. And then you have to fix it. Right? And so if it needs fixing. All right. So you look at this and you look at your poles, right? And then you have, if you want to make it in control, you add a negative feedback. Okay. And then see what happens to it. And there's various names for feedback. K is proportional and it's just gain, right? That's just like the resistors, right? But you can also have something called derivative feedback, where you put like an op-amp circuit in between that takes the derivative. you can have integrative feedback where you put an integrator in the feedback loop, which is what we've done with the DF2 filters. All right. And so this isn't really today's thing, right? But just to see where you're headed is if we have a system here where we have some constant divided by S minus this number, right? It's on the right-hand side. We put in this feedback system and now we have a new system, Q of S, right? YS is still the same, but it's no longer just H of S, right? And then we substitute in this value for K wherever H is, multiply through, right? And notice now I have this KA. And if I can make KA larger than P1, well, then I can turn it into a pole on the left-hand side. Now, sometimes proportional doesn't work and you have to use various things, all right? Now, to kind of show a system that the real part is 0, but there is a complex part, I want to talk about the LC system. And here, this 833 microhenries and 150 farads is from last time when we were talking about electromechanical systems, where this was a spring and this was a moving mass. But now the resistance is gone, right? The damper is no longer damping, right? It's broken, but not frozen. So what's the transfer function? All right, we take the voltage division just like we did last time. We go through just like we did last Monday. And now, right, we're missing an S term. Now, why that's bad, we'll talk about right now is let's look at the roots of the denominator. So the roots of the denominator are poles, right? And so B is 0, there's no B term, right? Since there's no S to the 1 power, there's no B, right? So it's -0 minus 4. Well, now it's basically we're going to get plus or minus omega j, okay? That's not good. So this will actually just be a sine wave, which actually sometimes you want. So this could also, if I had different values of L and C, that could be a resonant circuit that is picking out a frequency for a radio station where you want that to happen, right? So you don't always dislike systems that are out of control. Oscillators are very important, all right? But let's say in this case, we're doing an elevator and we don't want the elevator bouncing up and down. So if we follow this here where G of S is K, and then I have our H of S, well, here's my H of S right here, and then G of S is K. When I multiply it through and simplify, I get S squared plus K times omega naught squared plus omega naught squared. Well, there's no S to it. Doesn't exist, it's missing, right? So it'll still oscillate. It just oscillates at a different frequency. So we need to get that real part, all right? So now I have a KS term. I'm not saying how I'm going to get it. I'm just saying I'm going to have a constant times an S, right? So here's my H of S, here's my H of S, here's my G of S is now K times S. And when I multiply all that through, I still have my omega naught squared, but now I have K omega naught squared times S. Well, now I have a B term that I can make sure that the real part will be on the left-hand side. Now it still might be over, under, or critically damped, but now I can set the right value of K to make sure that this stays in control. Now, of course, how do you get that to happen? Well, you put a resistor there, but this is just a time plot of what's going on, is that I have a resistor. And yeah, if we look at stepping this parameter here, R is going from 1 milli to 100 milli. It's taking 2 steps per decade, right? So we see this kind of overdamped response. Right here, red is very close to critically damped. And then the blue, there's a little bit of overshoot. So that's underdamped. And then here's a lot of ringing, right? And so if we recall, for that particular system, so basically the bigger R, right, this R over L is that K over S that we're kind of adding in. And so the bigger R, right, the bigger this will be compared to this, and the more overdamped it'll be. So the smaller R is going to be the more underdamped. And now think about it. What if I had the smallest R is a milli? Well, what if I put a nano, right? Right now it's taking 8 seconds to stop oscillating. So even though technically it's in control, can you imagine being on an elevator that it takes 8 seconds by the time it stops, right? But then the elevator is going up and down until it takes 8 seconds to settle before the door opens. So theoretically you're in control, but that's not really, in that context, a usable system. And so many times some people will use a shorthand that being out of control means there's oscillations. So you have to be careful how people are talking, okay? On exams, I'm pretty clear, you know, I'm using the mathematical definitions of being in control or out of control. Right, again, Tower of Terror. So maybe I'm working for Disneyland and I'm trying to make a scary ride and I want it like that. But of course, it does have to dampen out eventually because, you know, you got to get people off and on the rides. So maybe it oscillates for a minute. Okay. So just some rules here, right? All the poles must be in the left-hand plane, because either you're going to get an integrator or exponential increase. Those are that's really what's going on, right? Examples of systems that aren't in control. Well, we talked about the integrator, the double integrator to whatever, right? Here we have what looks like a low pass filter, but that -10 gives us exponential increase, right? Here's a second order system, but there's no S term. And so we get 2 complex poles. It's not an integrator, it's an oscillator. So that's not in control. Here, which we haven't quite talked about yet, is that that minus sign here, right, will cause this is the quadratic equation and I put in a 0, right? If I put in a positive number, if B is positive, right, then minus B puts that pole on the left-hand side. But if B is negative, minus times a minus is positive, regardless of whether it's repeated, separate poles, complex poles, that pole is on the right-hand side, the real part. So, and then depending, right, you'll either have 2 exponential increases, 1 exponential increase. It's not going to work. Here, this is out of control as well. And this one. Right, okay. So Nick, to be in control, a second order system would either be over, under, or critically damped. But you can have a first order system that's in control, but there's no over, under, critically damped doesn't matter. You can have third, fourth, fifth, and sixth order systems that are in control or out of control, but they don't have the special name of over, under, critical. Higher order system, higher than second order, really you either have complex poles that cause oscillations if the real part is on the left hand side, right? So yeah, Rudy, you're right. What you just wrote is out of control. So Javier, the great question. So we have to make the transfer function stable. If you're asked to, if you're trying to make an oscillator, then don't make it stable. You'll ruin it, right? A system being out of control, it's almost like we're calling a value judgment that somehow being out of control is bad. And of course, I gave an example of bad behavior on my part, right? To you know, that kind of implies that being out of control is bad, right? But this is an example for another day. Okay. But, you know, if I have, and this is kind of a, let's call this a motorized wheel, right? And I, you know, my step response, I have 0 to 1, right? Into that system, right? What I can have, like the speed, right, is related to the frequency of rotation, right? And so if I'm plotting omega, meaning how fast this is spinning up, yeah, I could have this where I put in a step response, the motor spins up and then hits some constant value. But then if I integrate this rotation to get position, right, well, this wheel will always be spinning and my position will do, you know, something like this. I keep going, right? Well, I want to keep going, right? How do I stop going? Well, I have to turn it off, right? But there's nothing bad about that. But if the frequency, if I put an impulse response and the frequency didn't converge, right, that would be a real wild system to control. So you don't always have to do it. It's just when you want to do it, you have to know what the issue is. But that's a great question. Now, if it's first order, right, that's easy, right? S is either equal to 0 or it's not. If it's, or, you know, S is some negative number, or the pole is some negative number, you know, right? If the pole is 0, you can tell. Second order, you've got your quadratic equation, and really, you just put in those values, and if the real part is 0 or greater than 0, you're either going to get some kind of integrator or some kind of exponential increase. You're going to be out of control. All right. Now, what about higher order systems? You know, S cubed, something, 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 right? Well, again, we're really just worried about the denominator right now. So really, we just have some polynomial in S, and can we look at it and just tell, is this in control or out of control? And sure, there's a cubic equation, right? But in some ways, we don't really need to know what that pole is. We just need to know if it's in the wrong place, right? So there's something called Descartes' rule, which tells you the number of poles, and it's really kind of involved, right? To tell you the exact number of poles that are one place versus another. But here's the thing. We don't care how many poles are on the right-hand side. We just have to make sure there's no more than there's none, right? We got to make sure they're all on the left-hand side. That's actually really, really easy. So if you look at the denominator, as long as there's no sign changes in the constant and there's no missing values of S, then there'll be some real pole. There'll be like, there could be repeated real poles. There could be separate real poles. There could be complex poles or some combination of all the above, but it's going to be in control. It's actually that easy, right? In some of my old notes, I'm kind of going through the whole thing, but so really, what does this mean? Is if I have the denominator of S, and I have S cubed plus A1 S squared plus, right? Plus one, plus sign, plus sign, plus sign, right? S cubed, squared, S, no S. It's fine, right? If I have minus signs here, it's fine. It's in control, right? Now, what wouldn't be in control is something like this. Where I have a sign, or something like this. They all have to be here. Anything missing, and you're going to get at least one pole on the right-hand side, okay? Equal to or greater than the right-hand side. And if you have one change of sign, all right, so really, because we're not concerned with the exact number of poles and where they are, because to actually go through, it's quite involved. And sometimes you don't really know, right? It's very hard to determine, but you know you've got at least one, and one pole in the wrong place, right? If the real part of the pole is greater than or equal to 0, right? You either have an integrator, oscillator, or e to the plus t. And those things are systems that are not in control. Now you can make it more complicated than that, but I should say, right, on an exam or an interview question, and you're asked, why is this system out of control? And you say, well, there's a minus sign there. That's not really a good answer. Is that minus sign indicates that there'll be a pole on the right-hand side, which will either turn into an integrator, oscillator, or exponential increase, which is an out-of-control system that if you put in a step response, one of these things is going to happen. That's really a complete answer. All right. So if you're indexing this, I would really highlight that with an exclamation point. All right. So, and here's the thing. Oops. So right here's a minus sign, right? When I'm doing my control system, all I have to do is come up with a system that changes this to positive, right? Here I'm missing something. I just have to have a GS that adds it in. So really, you can quickly identify the thing that's wrong and quickly make a control system that that fixes the issue. God. Are there any questions? Okay. Well, I feel kind of guilty for letting you go 4 minutes early. Hey, Nick, why don't you send me an email? Because I have some things I have to do after class, and I'll take a look. But I think 10B is control, and we still have another day of controls where we're actually go through and do a lot of examples, okay? Like inverted pendulum and a motor and things like that. So Mike, that is a great question. Is there a relationship between poles on the left or right and high and low pass filters? So it's kind of hinting at that. So just for a first order, right, the pole is on the left-hand side, pole is on the left-hand side, and this is just a low pass filter. The step response of this is just going to be, you know, that, and it'll take 5 tau to get there. The step response of this is just that. But notice, you know, I'm putting in a step, it ends at a non-zero value, but it stays at a DC value. Okay. Now, this or this, okay, well, they're not really filters, right? These are really just exponential increase systems. And again, like 10B is controls, if I remember, and we still have Monday to go over controls, so it can't be due this weekend. All right. I thought I went through and made sure that everything was set up properly for the rest of the semester. Okay. And so to continue this, right, the step response of this is this, and it takes 5 tau. Here, it's just the opposite. This is like you have an inverting amplifier, right? But again, this here, regardless of what's going on up here, I'm going to get some kind of exponential increase, right? The magnet, you know, positive direction or negative direction. Same here. It really doesn't matter. This is causing exponential increase. So, you know, a filter, you know, the filter is in control if you designed it properly, right? And what's really interesting is DF2 is made out of things that are out of not in control, but because it's in a negative feedback network, the whole transfer function is in control. Right. Oh, these are great questions. And now you can't leave. So we've talked about the low pass. This is low. This would be high. Or I should say, the numerator, right? Omega naught squared, low. S squared, high. Band. Notch. 4 different numerators, same denominator, and the step response, right, of the low we've done, right, it's something like this. Now, sure, it can be over critically or under, but it starts and ends at 0. The high, right, is going to do something like this. Right, it might dip below, it might not. The band, right, will do I'm not really drawing it well, but it'll come up and come down. And then the notch will do something like that. So the low ends at a non-zero value. The notch ends at a non-zero DC value. The band, the high and the band end back at 0. So all of them are in control. All right. And so these filter functions, low, high, band, and notch, right? And filter topologies, right? With like Butterworth and the other ones. And then filter implementations like multiple feedback, DF2, RLC, right? If done properly, right? You could always put a wire wrong, right? And especially in DF2, right? if I put this here, oops, right, I'm actually changing the sign of that first term. And so this, and I'm not drawing everything else, this will be out of control. So that's what I mean by, just because I call it a filter, well, calling it something doesn't really make it so, right? I could wire something back accidentally. So those are really insightful questions. Okay. So anyway, that was 4 extra minutes. Take care, everybody. I know it's time for you all to scoot.
You too. Have a good weekend.
All right, you too.
Thanks, see ya.